Welcome to the fifth program on electromagnetics. In the previous program, we had talked about energy, potential and potential difference, electric dipole and energy density with respect to electrostatic fields. Today, we shall be talking about current and current density, metallic conductors and their properties, continuity of current equation and boundary conditions, which would be including method of images. Now coming to current and current density, we shall start with convection and conduction currents. In the previous section, we had talked about potential, and today we will talk about the second important parameter in electrical engineering, which is current. The current through a given area is the electric charge passing through the area per unit time, that is I is equal to dq by dt. The concept of current density is now introduced. That is, if current del I flows through a surface del S, then the current density is given by Jn, which is equal to del I by del S, or del I is equal to Jn into del S. Here we have assumed that the current density is perpendicular to the surface. If the current density is not normal to the surface, then del I is equal to J dot ds, or if we integrate it, then I is equal to integration of J dot ds. Equation 5.3 shows that current I through S is nothing but merely the flux of the current density J. Now, depending on how current is produced, we have three different current and current densities. First is the convection current, second is the conduction current, and the third is the displacement current. In this program, we shall be talking about the first two currents. First of all, we take the convection current. Since the convection current does not flow through a conductor, it does not obey the Ohm's law. It occurs when current flows through an insulating medium such as liquid, rarefied gas or vacuum. A practical example of convection current is a beam of electrons in a vacuum tube. Consider the filament shown in figure 5.1, where it can be seen that it has volume charge density of rho v and the charges are moving in the direction of y, that is u is equal to uy into ay, and from this we can find the value of the current as del I is equal to del q by del t, which can be expanded to rho v del v upon del t, which can further be expanded to rho v del s into del l by del t, which is equal to rho v del s del l by del t, which finally equal to rho v del s uv. The y directed current density is therefore given as Jy is equal to del I by del s, which finally comes out to be rho v into uv. In general, we can represent the current density as J is equal to rho v into u. Second, we have the conduction current. Since the current now flows in a conductor, therefore it obeys the Ohm's law. The conductor is characterized by a large number of free electrons that provide conduction current when we impress an electric field. When an electric field is impressed upon an electron having charge minus e, the force upon it is given by F is equal to minus E into E. Now, the electron is not free to move in the space, and therefore it will not be accelerated under the influence of the electric field. Instead, it suffers constant collisions with the atomic lattice and drifts from one atom to the other. If the electron has a mass m and is moving in electric field E with an average drift velocity u, then according to Newton's law, the average change in momentum of the free electron must match the applied force, that is m u upon tau is equal to minus E into E, which results in the velocity being equal to minus E tau by m into E, where tau is the average time interval between collisions. If we have n electrons per unit volume, then the electron charge density is given by rho v is equal to minus n into E, and therefore now J becomes equal to rho v into u, which finally gives us as J is equal to conductivity into E. This is nothing but the point form of Ohm's law. Next we come to conductors. A conductor is one which has one or more electrons per atom which are free to roam about throughout the material. A perfect conductor would have infinite or unlimited supply of completely free electrons. Now, the basic electrostatic properties of conductors are: number 1, the electric field intensity inside a conductor is 0. The volume charge density rho v is equal to 0 inside a conductor. Any net charge will reside on the surface of the conductor. A conductor is an equipotential, and outside a conductor E is perpendicular to the surface. Now, in the figure 5.2, when we apply an electric field EE, then we see that the positive free charges will move in the direction of the electric field, while the negative charge would move in the opposite direction. This charge migration is very fast, and the free charges, they do two things. Firstly, they accumulate on the surface of the conductor and form an induced surface charge. The induced surface charge, they then set up an internal field EI, which cancels the external field EE inside the conductor. That is, inside the conductor, the net electric field is 0. This leads to an important property of a conductor, that is, a perfect conductor would not have any electrostatic field in it. Also, the conductor is an equipotential body, that is, gradient of V is equal to 0 inside a conductor. Now, if some charges are introduced in the interior of such a conductor, then all the charges would move on the surface and redistribute themselves quickly in such a manner that the field inside the conductor vanishes. According to Gauss's law, if E is equal to 0, then the charge density must also be 0. Procedure for deriving the resistance of a conducting material. In the last case, the conductor was isolated, but in figure 5.3, the conductor is not isolated, it is connected with a battery, and therefore there is no static equilibrium, the conductor is not isolated, and the electric field inside the conductor is no longer 0. As the electrons move, they encounter damping forces known as resistance. Now, from the figure we can see E is equal to V by L and current density J is equal to I by S. Also, from point form of Ohm's law, we have J is equal to conductivity into E. Therefore, from these equations we get I by S is equal to conductivity into V by L, and solving that we finally get R is equal to rho L by S, where rho C is nothing but the resistivity, which is equal to 1 upon conductivity. The equation 5.15 is applicable when the cross section of the conductor is uniform. However, if the conductor cross section is not uniform, then we have to use R is equal to V by I, which is equal to integral of E dot dl upon integral of J dot ds, which can further be expanded to integration of E dot dl upon integration of conductivity into E dot ds. It should be noted that the negative sign before V is equal to minus E dot dl is dropped, because integration of E dot dl is less than 0 if the current I is greater than 0. Next, we come to the expression for power and power density. Now, power is equal to work upon time, which is equal to force into distance upon time, which can further be expanded into force into distance upon time, which is equal to force into velocity, and therefore P can be written as F dot U, which when expanded is equal to QE dot U, which when further expanded finally gives us integral of E dot J dV, or the power is equal to volume integral of E dot J. Differentiating equation 5.18 with respect to the volume, we get dP is equal to E dot J dV. dP by dV is equal to E dot J, which is nothing but the power density, or the power density is equal to E dot J, which can be modified as E dot conductivity into E, which is equal to conductivity E square. Next, we have the continuity equation and relaxation time. From the law of conservation of charge, we know that charge can neither be created nor destroyed. However, equal amount of positive and negative charges can be simultaneously created, destroyed or lost by recombination. The continuity equation is based upon this law of conservation of charge when we consider any region bounded by a closed surface. The current I out through a closed surface S is given by equation 5.20, which is I out is equal to the closed surface integral of J dot ds. Now, the outward flow of positive charge must be balanced by a decrease of positive charge or an increase of negative charge within that closed surface. If the charge inside the closed surface is denoted by q in, then the rate of decrease is given by minus dq in by dt, and from the principle of conservation of charge, it says that I out, which is equal to surface integral of J dot ds, will be equal to minus dq in by dt. If we apply divergence theorem, that is, we apply divergence theorem to the surface integral, then it gets converted into a volume integral, and that finally gives us minus dq in by dt, which is equal to minus integral of del rho v by del t into dv. When we compare them, we get del dot j is equal to minus del rho v by del t, which is nothing but the continuity of current equation. Now, the physical significance of this is that it means that the current or charge per second diverging from a small volume per unit volume is equal to the time rate of decrease of charge per unit volume at that point. The continuity equation essentially states that charges cannot be accumulated at any point. For steady currents, del rho v by del t is equal to 0, that is, the divergence of current density is 0. Hence, del dot j is equal to 0 shows that the total charge leaving a volume is the same as total charge entering it. Next, we have the relaxation time. Now, we have three equations. The first is the point form of Ohm's law given by equation 5.26. The second is the Gauss's law, and the third is the continuity equation. Using these three equations, we get equation 5.29, which is del rho v by del t plus conductivity upon permittivity into rho v is equal to 0. This is a homogeneous linear ordinary differential equation which can be solved by separation of variables, and on doing that we get del rho v by rho v is equal to minus conductivity upon permittivity into del t. If we integrate both sides of the above equation, we get equation 5.31, where we get a constant. To find the constant, we have to apply the boundary conditions. The boundary condition that would be applied is at t is equal to 0, rho v is equal to rho v naught, or the initial charge density, and from that we find the value of the constant c, which comes out to be the ln of rho v naught. Putting this value of c in equation 5.31, we finally get the value of rho v is equal to rho v naught into e to the power of minus t by the relaxation time Tr, where Tr is equal to permittivity upon conductivity. The equation 5.32 shows that as a result of introducing charges at some interior point of the material, there is decay of volume charge density rho v, and associated with the decay is charge movement from the interior point at which it was introduced to the surface of the material. The Tr, which is also known as relaxation time or rearrangement time, is the time it takes a charge placed in the interior of a material to drop to 36.8% of its original value. The relaxation time is short for conductors while it is long for dielectrics. Next, we have the boundary value problems. Now, the electric field, it can be determined by two methods. One, by the Coulomb's law or the Gauss's law when the charge distribution is known, and the second method is E is equal to minus gradient of V when the potential V is known throughout the region. But it often happens that neither the charge distribution nor the value of V is provided. In such problems, determination of E and V throughout the region can be done by two methods. First is by using the Laplace and Poisson's equations, and second is the method of images. The problems mentioned above are referred to as boundary value problems. Here we shall be discussing the second method, which is the method of images. The method of images was introduced by Lord Kelvin way back in 1848, and this method is commonly used to determine V, E, D, rho s due to charge in the presence of conductors. By this method, we avoid using the Laplace or Poisson's equation, but rather we utilize the fact that a conducting surface is an equipotential. Although the method does not apply to all electrostatic problems, it can reduce a very difficult problem into a very simple one. The image theory, it states that a given charge configuration above an infinite grounded perfect conducting plane may be replaced by the charge configuration itself, its image, and an equipotential surface in place of the conducting plane. We can see typical examples of point, line and volume charge configurations and their images as can be seen in figure 5.4. The charge q has its image on the other side as minus q, rho l has its image minus rho l, and minus rho v has its image plus rho v. In applying the image method, we have to make sure the satisfaction of two conditions. Firstly, the image charge must be located in the conducting region, and secondly, the image charge must be located such that on the conducting surface the potential is either 0 or constant. The first condition is necessary to satisfy Poisson's equation, while the second condition ensures that the boundary conditions are satisfied. In general, when the method of images is used for a system consisting of a point charge between two semi-conducting planes inclined at an angle phi, then the number of images is given by the equation n is equal to 360 by phi minus 1, because the charge and all its image would lie on a circle. For example, when phi is equal to 180 degree, then n would be equal to 1 as can be seen in figure 5.5. When phi is equal to 90, then for one charge there would be 3 images, and if phi is equal to 60 degree, in that case there would be 5 images as can be seen in figure 5.5c. Now we will apply the image theory to a particular problem, that is a point charge above a grounded conducting plane. Now consider a point charge located at a distance h from a perfect conducting plane of infinite extent as can be seen in figure 5.6a. The potential at the grounded point is V is equal to 0. The electric field at any point P x, y, z is given by the sum of the electric field due to the charge itself and E minus due to its image, which is equal to q r1 upon 4 pi epsilon naught into r1 cube plus minus q r2 upon 4 pi naught into r2 cube, which is given by equation 6.41. Here the distance vectors r1 and r2 are given by equation 6.42, that is r1 is equal to x, y, z minus h, and r2 is equal to x, y and z plus h, and therefore E becomes equal to given by equation 6.44. It should be noted that when z is equal to 0, E has only the z component, confirming that E is normal to the conducting surface. The potential at P is easily obtained using equation 6.41 or 6.44 using the expression V is equal to minus integral of E dot dl. Thus, V is equal to V plus V minus, and when expanded we get V is equal to q upon 4 pi epsilon naught into 1 upon x square plus y square plus z minus h whole square under root minus 1 upon x square plus y square plus z plus h square the whole under root for z greater than or equal to 0 and v is equal to 0 for z less than or equal to 0. It should be noted that at z is equal to 0, the value of v is equal to 0. Now the surface charge density of the induced charge can be obtained from equation 6.44 as rho s is equal to dn, which is equal to epsilon naught into En at z is equal to 0, which when solved gives us equation 6.46, that is minus qh upon 2 pi into x square plus y square plus h square the power 3 by 2. We can also find out the total induced charge on the conducting surface as qi given by equation 6.47. By making a small manipulation, that is by changing the variables, rho square is equal to x square plus y square, and taking the area dx dy into the cylindrical form, that is rho d phi, we get expression 6.48 for qi. Integrating over phi gives 2 pi, and letting rho d rho equal to half d of rho square, we obtain expression 6.9, that is we get an expression for qi which comes out to be minus q. And this was expected because all the flux lines terminating on the conductor would have terminated on the image charge if the conductor were absent. In this program, we have discussed current and current densities, where we enumerated convection current, conduction current and displacement current, and we had discussed the first two. Then we talked about the metallic conductors and their properties, which was followed by the continuity of current equation, which is based on the law of conservation of charge. And finally, we talked about the boundary conditions, where we talked about the method of images. I hope you have enjoyed this lecture. Thank you.